So now we're going to continue with the lecture on Unit 7, Construction Materials, the types and their uses. So one of the things that we want to make sure that we achieve is be able to identify the variety of basic materials used in construction and be able to identify the components, the basic components of concrete. Describe the different types of masonry, brick, block, and mortar, and classify wood as a hardwood or softwood. Be able to recognize different structural steel shapes. Be able to describe various types of glass, plastics, and insulation. Identify symbols representing materials on a drawing, and explain the fundamentals of green building in construction. So some of the technical terms. Admixture, something that you see typical in concrete work. Adobe brick. Adobe brick is a type of brick made from natural earth, consisting of clay. You could say dirt if you want. Aggregates, they refer to rocks that have been classified into specific sizes. So you can have 3/4 inch aggregate, 1/2 inch aggregate, 3/8 aggregate, 1/4 inch. But basically what they call classified, clearly organized, specified size aggregates. Angles, for typical angles, are like 90-degree angles, 45-degree angles, 30-degree angles, 60-degree angles. Being able to just look at an angle and know roughly what it is. Ashlar, bent glass, bond. What does it mean? A bond beam, brick masonry, building brick, cement, ceramic tiles, concrete, concrete brick, concrete masonry unit, or CMU. Cut stones, face brick, and ferrous metals. Fire brick, fire clay tile, flexible insulation, float glass, gauge system. So for example, the gauge system is a system of measuring thicknesses or gauges, and usually metals are used the gauge system. Information about glass. What is glass block? What is glazed brick? What is gravel? Green building. What is grout? What is a header course? What is hydration? What does it mean for insulating glass? Or kiln or burnt brick? Or laminating or lintels? Laminating, for example, is a way layers are glued together through a laminating process. Lintels is a piece or a component of material in a window opening. Technical terms. Loose fill insulation. We've already talked about insulation. What is loose fill insulation? Lumber, mortar, mosaic tiles. So we spoke about tiles. What is a mosaic tile? The difference. Non-ferrous metals. We've got your ferrous metals and your non-ferrous metals. Being able to know what that means is important. Open web steel joist. What does it mean for something to have an open web? Steel joists have open web. I'm sure there's other situations where you're going to have that open web. What is patterned glass or paving brick? What does it mean for concrete to be pervious? What is a pervious concrete? Or plywood or quarry tile. Lots of references to tile I've seen in these. Reflective insulation. So another type of insulation. Reinforcing bars. Rigid insulation. Again, another type of insulation. Rough sawn lumber. So it's lumber, but that's prepared in such a way that it's rough. You can still see the saw marks. Rubble. What is rubble? What is the difference between rubble and aggregate? Do you know? R value. All this talk about insulations, insulation is something that has an R value. So knowing what an R value means and what does that mean for different types of insulation. We spoke about glass and different kinds of glass. One type of glass is called safety glass. So what is safety glass? Sand, lime, brick. We've spoken about lots of different bricks like adobe. What's a sand lime brick? Single white walls. What is that? Stained glass. What's the difference between stained glass and safety glass? Stone masonry. What's the difference between masonry and bricklaying? Stretcher. What is a stretcher? Where is it used? Why is it used? Structural clay tile. What is structural clay tile? What makes it structural? Like steel. We have structural steel. What makes this steel structural? And what makes it so unusual that it's given this specific name, structural? Surfaced lumber. We've talked about other kinds of lumber. What like rough sawn lumber. What's the difference between that and a surfaced lumber? Sustainability. Sustainable design. Something that is designed with an intent to maintain a certain sustainability. So terracotta. What is terracotta? Where is it used? What's it used for? Just so some are aware, it's a type of clay tile. Thermal insulation. We've spoken about insulation, different types. What is thermal insulation? What is a welded wire fabric or a WWF? What is wythe? Okay, so having spoken about all of those different definitions and all those different terms, let's see where they might be used. Aggregates. What are aggregates? They're also referred to as gravel. They're used in many construction applications. They provide support for a subbase. They provide backfills in foundations. They help provide drainage underground. They fill around pipes. They are the ingredients for concrete. So you can see here aggregates being used in its different forms, right? As a subbase, it's being this machine, some sort of tamping, compacting machine, making sure that this surface is solid before concrete floor gets poured over it. Here you can see the piles of aggregate that are being accessed by a backhoe tractor. Here you see an area that's covered with aggregate with inside the footing of a form. So this aggregate to be the base of what would later have a concrete slab over it, over the top. So looking at some symbols here, these are these are illustrations of what aggregate would look like, or symbols of aggregate to be used in drawings. So here they call this riprap, which is probably some big, larger pieces of rocks, not necessarily the size of boulders, but not the size of aggregate, being held in place by what they call here as a head wall, or maybe a retaining wall. But you can see that this head wall is holding back some of this or all of this rock. When we look at this illustration here, pea gravel and sand in a section view, we can see where there's layers. There's this finer level of rock called pea gravel, and then there's a layer of sand. So they're just circles of different sizes and little dots of sizes. Again, these are symbols of what we would see in a section view. This would be a plan view of a driveway. If I was looking down, this is the concrete driveway, and it spreads out and gets wide as it gets close to the street. This symbol here is just showing you that it's a brake line. So this driveway continues in this direction. We just don't see it going there. So this is gravel being illustrated on a gravel driveway plan view. This is another section view showing you crushed gravel in a section. So we can see, oh, and this was a plan view of a rip wall. So we're seeing the material being held in a plan view, so it's spread out over the surface, and these dotted lines or hidden lines represent what's underground. So fine aggregate, sand, small particles of 591 thousandths of an inch, or 0.187 inch diameter. So it's from 5 thousandths to 0.1875 in diameter. That's considered sand, the small particles within that size spectrum. Then from there you have what is referred to as pea gravel, small rounded pieces that are from 1/4 inch to 3/8 inches in diameter. In your fine aggregates, your sand, you see here's an illustration of the sand. There's an illustration of the gravel. River gravel is large aggregates dredged up from river bottoms. Crushed stone is stone that's mined mechanically and fractured to size. Okay, so in your two different coarse aggregate types, you have river gravel and crushed stone. River gravel is exactly that. It's rocks that tumble down a river. And rocks that are dredged from river bottoms or extracted from rivers, they're going to be rounded and smooth. Whereas stone that's mined mechanically could be from drilling and crushing, or using explosives like dynamite to mine and extract the rock, so it's fractured, it's broken to size. Whereas river rock is the size from the years and years, hundreds of years or thousands of years of the rock tumbling in a river. And stone hitting upon other stones is what breaks them into smaller stones or smooths stones from sharp edges to smooth edges. So rivers do that, whereas mines have the coarse fractured. So just remember that's the difference between river and crushed stone. Is one is fractured and the other is naturally smoothed. So the characteristics of aggregate: the soundness, right? How solid it is. Its stability, chemically speaking. Its ability to withstand abrasion, grading and sieve analysis, percentages of particles, the shape of the particle, the texture of the surface, the specific gravity, its absorption ability, its moisture content, and its volume stability. Those are different characteristics. So Division 3 under CSI format is concrete. So when you're looking at specifications in the specification manual with regards to concrete, Division 3 is going to discuss it. Concrete, little history, used by the Romans as early as 100 BC. Concrete is a mixture of cement, sand, and coarse and fine aggregates and water. Hardening is caused by a chemical reaction between the cement and water called hydration. And most mixtures set in 4 to 12 hours. So there's a curing process in this hydration, this chemical reaction. Hydration is a curing process where the material will activate, begin to heat up, and cause the moisture to evaporate, and the material will turn from a liquid state, which is what you see here, into a hardened state where it becomes solid. Hydration is a process affected by temperature, so reactions slow below 70 degrees and completely stop around 32 degrees. So if it's freezing outside and you're pouring concrete, that curing process won't happen. So it starts to slow down below 70 degrees. Too much water reduces the strength. So when you're mixing concrete, you want to mix your sand, your aggregates, your cement, and your water in the appropriate ratios. Adding too much water will only weaken the strength. So once concrete has become active and it starts to harden, and you think adding water will extend that, you won't make it slow down its process. So once it starts to harden, it's going to harden. You adding water is only reducing the strength and affecting the quality of your concrete. You'll actually ruin the concrete by adding water to it. Types of cement. You have your 5 basic types of cement that include type 1, which is your normal cement, type 2, which is a moderate sulfate resistance, and type 3, high early strength, type 4, low heat of hydration, type 5, high sulfate resistance. So each of these types has their particular reason to be used in application, and usually will be called out in the specs. Type 1 normal Portland cement is a general purpose cement commonly used in construction. So in your specs, they may be calling for type 1 normal cement, but they may be calling for type 2. So being aware of the type of cement you're going to use in your structure and your construction is very important. Otherwise, you may have to abandon that material remove it and reinstall it. And removing concrete and replacing it is not something that is taken lightly. So we have your concrete mixture is made up of proportions. So if we had a cubic yard of concrete and we were to separate all the materials by its percentage, 15% of it would consist of water. Then air entrapment, the little voids, the little spaces can be anywhere from 1% to 5%. So it is possible that concrete can have larger air entrapment, but it's during the installation process, if it's done right, you'll minimize the air entrapment. Coarse aggregates represent 45%. So just under half of the concrete is made up of rocks already, pre-existing aggregates, plus fine aggregates. So you've got coarse and fine aggregates, and then cement, which is the cement binds all of those materials together. So you have coarse rocks with a little air, a little bit of water, some sand, all mixed together like a cake mix, and the cement being the flour. Mix all the ingredients together, then you get your final product, which is the concrete of a specific strength. Sometimes we have to add mixtures to concrete. The add mixtures are things like retarders. They're used to slow down the set time. So it's a hot day. It's not cold outside. It's well into the 90s. So we know that the concrete will cure. We said that it'll cure in 4 to 12 hours. Well, that's also dependent on temperature. So what if we wanted to cure closer to 12 hours and less than, and farther away from 4? We'd use retarders. Or maybe we're working in colder temperatures and we can't wait 12 hours for the mixture to solidify. So we use accelerators to speed up the set time. Sometimes we use water reducers, used to make concrete act like it has more water than it does. See, we can't add too much water or we affect the strength. But we might want it more liquidy. We want it more loose. So we'd have to use some sort of water reducer. Something that acts like water, but then is not water, so it doesn't affect the strength. Green building, or the use of fly ash. Fly ash is produced when coal is burned to generate electricity. So fly ash is what they call a byproduct. It's the waste. And when you have fly ash, when you have a waste from coal or from any type of process, and it builds up, people try to come up with alternate uses of this waste material, this byproduct. So fly ash has been found to be used in concrete, and it provides environmental benefits. It creates a more durable final product. So where you'd have some sort of waste now has a use in a process of making concrete more durable. So when you're able to do that, that's green building, right? Taking some material that would normally not have any value or be considered a waste gets used in a product, and it's good to the environment because you're taking a waste and putting it to use. Concrete reinforcement. So concrete is very rigid. One of the strengths that it has is it has good compressive strength, but it's poor tensile strength. So it's good at holding a lot of weight, but it's not good at being able to bend or be flexible. So if you're able to use reinforcing steel, that helps overcome some of the weaknesses in the tensile strength. The deformations in rebar help improve the bond with the concrete. So just like aggregate can be mined and it's like fractured and rough or smooth from a river, it's mixed in there. But in being able to bond with concrete, be able to be part of the concrete mix, the steel has ridges, it has deformations. If you ever look at it, it's got little lines and checks that it's not a smooth round bar. Has deformations on it. What that does is it allows it to get trapped in the concrete, that it can't move. Once it's encased in concrete, the bar is trapped in there, and because of its shape, it's not allowed to move. And because it doesn't move, it helps improve the bond with the concrete. Bars are set in place prior to casting. So remember, before casting, we have empty space. So we set the bars in place, and then we cast, or we pour the liquid concrete and have it flow around and to help bond with the bars. The larger the bar, the greater the tensile strength. So if I have lots of steel or some thick bars of steel in the concrete, I can improve the strength of that concrete. See, this is those deformed, these ridges. It looks like a cross pat. This looks like a screw pattern or a cross hatch. But you can see that it's got all these different unique shapes to it of the different size bars. So once it's encased in concrete, it's locked in place. It doesn't want to move around. It's trapped. So number 3 bar refers to the size of bar. Number 4 refers to a 1/2 inch. Number 5, 5/8. Number 10, 1 1/4 inch. So if I go to number 10, it's 1 1/4 inch. If I go to number 5, it's 5/8. So a bar number is by eighth inch equal bar sizes. So 3/8 to a 1/2 to a 5/8 to 3/4. These are 1/8 inch increments. 7/8 to an inch to an 1/8. Hence the bar sizes. Reinforced bars. This is a concrete. You can see it's liquid over here. You can see down below all the concrete that's going to be filled in this space. You can see up here there's forms, and with these walking platforms, you can see guys walking on the planks up above, and the concrete that's getting filled in down below. And all the concrete reinforced. You can see that the bars overlap each other. They're hooked to each other. They're tied to each other. So somehow they're connected in such a way that once they're filled, the void is filled with concrete. All these steel connections they become connections in the steel, and they provide reinforcing strength to the concrete for them to not only hold large amounts of weight, but be able to do it structurally. Here you see a wall that's reinforced with bars. You see down below that pre-wall, or the bottom section of the wall, has already been started. And then you've got steel bar coming out, and a wall will be put in its place here shortly, and will be cast around these steel bars. Here you see the forms of a wall, the empty space with the bars the reinforcing bars in the space waiting for it to be filled with concrete. This one are the bars, but with no forms yet, right? So these are the forms already around the bars. Welded wire fabric. So what you can see here in this illustration is wire that crisscrosses each other in a pattern like 4x4. That's called a fabric. And that also provides reinforcing. You can see here in this illustration, this section shows you the earth, the aggregate, the concrete, and the wire that's embedded within the concrete. So you can see that this space from here to here, from the top surface to the lower level, roughly say 6 inches in thickness, halfway in between this wire. So you see this wire laying on the surface being poured with concrete, but what someone will do after is reach into the concrete and lift and pull the wire up and get it to float in the center. That's not always allowed. Sometimes you have to put spacers under the wire to have it already up in the air to be filled underneath. So right now, this wire is not, mesh is not doing the job that it would if it was laying inside the concrete, whereas that it's at the bottom level down here. So this wire mesh will is not finished. It will be relocated. It'll be grabbed and pulled and raised in that pool of liquid concrete. So smooth wire is fabric. So the W, deformed welded wire fabric with a D. So a deformed fabric wire will have deflections in it to help lift it off the ground so it doesn't lay flat on the ground, and that you don't have to manually pull it up. It's already, because of the deflections or the deformed shape of the wire, a wire may be bent to push and hold it already up. So wire fabric comes in widths and lengths. So your overall width, your overall length. So a 6x6 is telling you that you've got spacing of wire. It's 6x6. You've got your longitudinal wire spacing, your 6 inches, and then the second transverse spacing is 6. So this is just saying 6x6, so 6 inches in one direction, 6 inches in another direction. So it's not uncommon to have rectangular shaped wires like 3x6 or 6x3. W1, the W referring to a smooth wire. 0.4 referring to the longitudinal wire size. So 0.4 being the actual wire size. So W 1.4 by W 1.4. So it's wire 1.4 by wire 1.4. So you could have different thickness wires going in different directions. So this is how welded fabric is identified. Common stock styles of welded wires. So in that previous was an explanation of the wire fabric and how the size is broken down. You have your longitudinal, your transverse, your sizes overall. Here, showing you all the different sizes and designations. So you have multiple 6x6s, you have multiple 4x4s. In the olden days, they used to do it by steel wire gauge. Now they do it by W number. So they're showing you the relationship of the old way of designating it and the new way of designating it. And This tells you about the area that gets covered and the weight in pounds per square foot. So frequently referred to in the field as pounds of mesh. Because the wire is made up of a certain size and a certain shape, then you know that if I have a certain square footage of material, it's going to have a certain weight to it. So this 6x6 W1.4 by W1.4 is going to be about 21 pounds per 100 square feet. Not per square foot, so per 100 square feet. So if I had 100 square feet of another material, it's going to weigh 85 pounds. Division 4, masonry. Different types of bricks, right? In that technical terms, we saw CMU, we saw brick, we saw clay tile, we saw fire brick and stone. All of this is a type of masonry. All of this falls under Division 4 for masonry. Building units with many applications in construction. You got building brick, face brick, glazed brick, fire brick, paving brick, concrete masonry unit or CMU, clay tile, stone. So CMU, concrete masonry units, are a type of concrete block that is assembled using a mortar, and then the hollow areas, it has hollow areas to allow for bars, reinforcing steel bars to be able to be inserted both vertically and horizontally, and then the empty cavities filled later with concrete. So they are like a form. They provide space for reinforcing and building of the different shapes that you want. They stack like bricks, but they're hollow. They're empty. This example of clay tile, fire block, to me, I don't think that's a tile. I think that's some sort of reinforced brick, but that's my opinion. I could be wrong. Another Division 4 is masonry. This is just showing you better examples of here brick being applied like a brick veneer to exterior wall. Here you see it being used to create the wall, where this is a veneer to or part of a wall system. So there's might be plywood, plywood behind there, and wood framing, whereas this concrete blocks can be used for creating the structural wall holding up the building. Masonry mortar. Type M is a high compressive strength and good durability. Type S, high strength with stronger bond. Type N, medium strength for general use. Type O, low strength for interior non-bearing masonry. Type K has very low strength and should be used only for interior applications. So when you mix mortar, the cost of your mortar can vary by the type of mortar you're trying to create. So if you want something that's high strength, you're going to be using the more of a certain material, more aggregate, more cement, or you want to do something that's more for looks and not necessarily meant to have a high strength, because you're going to use it more for aesthetics, for looks. So maybe a type K would be more acceptable. Why you don't want to use type K for something that's going to be holding up a building, but you don't want to use something that's intended to hold up a building just to make the for its looks. So being able to understand the different types of mortar, when they're used, when they're necessary, is important. Types of bricks. So you've got adobe, which is made from clay or earth. You've got kiln burnt, which is basically a clay that's molded into shape and then fired to a hardness. You get sand, lime, you made from mixtures of sand and lime, and it's hardened under steam and pressure and heat. You have concrete bricks, which is made from Portland cement and aggregates molded and chemically hardened. So CMU wall, or CMU, is a man-made brick, or made from concrete and cement. Building bricks are usually referred to as common bricks, and they're used inside the building, outside the building. We have types of bricks. Bricks that are meant for faces, for facing, or a veneer. They're manufactured under more controlled conditions, and they're used to produce the bricks of specific dimensions, colors, and structural qualities. So they're facing bricks, right? So they're manufactured to have a look, a feel, and have certain structural qualities to them. Glazed bricks are finished with a hard, smooth coating on the face. So glaze or glazes usually is part of that kiln where you're firing or burning a brick. You'll maybe put a glaze on, so when it finishes, it has a glass or a finish or a hard, smooth coating on the face. Fire brick is a type of brick that is used to withstand high heat conditions, like a fireplace or an oven, a pizza oven, for example. You may use brick to make the chimney of a fireplace, but you may use fire brick to line that actual area that is exposed to the high heat and the high temperatures. So it's used where masonry units are exposed to the extreme heat. Paving is used on driveways and patios, and it can be decorative. So these are some symbols that we might see in drawings of brick. Small scale brick, large scale brick. See how you've got just plain horizontal lines. Here you have a brick pattern where they alternate and they stack and they alternate. Here this is a stone veneer or a rubble veneer. It's just showing you the look that you're trying to achieve. You notice here these horizontal lines of different sizes to stack up and making an unusual pattern. Here, this is the pattern of a concrete block, or this is the pattern of a wall that's just cast in concrete, just a plain flat. Notice that this tile looks like block, or this tile can be larger tiles, rectangular tiles, almost giving the appearance of concrete block. So you'll often see these symbols in sections or elevations so that you have an idea of the material being used on the space. Again, these are just different hatchings that are used in the symbols, just to give you an idea of the different materials being used. Patterns, whether it be color or shape, you have common bond, running bond, the English bond, the stacked bond, Flemish bond. Notice they all have unique patterns to them, but they're bonded together, so they're done not only for the structural, but they're also done for aesthetics, for looks. Bricks can be positioned, right? And the terms that they use: stretcher, header, sailor, soldier, Rodwick. So you can see that in this sailor pattern, you can see they're turned sideways and you see this facing. So here you see this soldier pattern where they're standing skinny and side by side or back to back. Or here they're standing tall side by side. The Rodwick pattern shows that the blocks, they alternate. They go from two the long way and then one in a cross pattern. Yet they still stand tall. They're not laying flat. Here, your standard stretcher, they're laying in their typical classic stretcher pattern or brick pattern, right? Very just the traditional pattern what we're used to seeing. It's called the stretcher. This is called coarse. I'm not sure what the difference between coarse and stretcher is in this particular situation. Single width is just showing you that the bricks are being used as the wall. So they are single width. The bricks are the wall. Here, the bricks are used in combination as a composite. They're used with some other type of block and in a pattern, and this is what's referred to as a composite, right? So you've got two different types of brick and then a pattern that locks them down at the header course. And the header usually is considered like an opening. Here you have two courses with an empty cavity or a moisture barrier rear wall. So you have the main wall and then the rear wall and air space. And then you've got steel that not only provides a spacer, but it's like a mesh, right? It's steel material laid in between the materials, the layers, to tie the walls together. Here this is done as a veneer. You can see these three, the brick is supported by a concrete foundation, directly supported underneath. Here, and the wall, the concrete is the wall. In this particular case, the brick is used in combination with a wood framed wall. So there's sheathing and framing behind it, and the veneer, meaning a layer, providing the outer layer of brick, but the inner layer of the wall is made up of wood framing. Concrete masonry units, the CMU blocks. They're formed from Portland cement, sand, and gravel. They're made in a factory setting, and then they're prepared in a variety of sizes and shapes and densities to meet construction needs. Standard blocks consist of 8 by 8 by 16, which in actuality is 7 5/8 by 7 5/8 by 15 5/8. That being said, when you take into account the mortar space, so 7 5/8, the 5/8 and 8. So the remaining 3/8 of an inch space would represent the mortar. So 3/8 inch, and usually 3/8, yeah, it's about 3/8 of a half-inch space that you would use for mortar that would get you your overall spacing of 8 by 8. Here's the structural clay tile. So they called it clay tile in a previous, but it's a structural clay tile. So it's similar to brick, but it's larger. It's a larger unit with rectangular open cells, you see. But it provides structural support. It has load-bearing capabilities. And then it's a backup for curtain walls, or fireproofing for structural steel. Stone masonry, right? Common materials, granite, like granite countertops, limestone, slabs, marble, sandstone, slate. All of these materials can come from a quarry that are stones that are cut and prepared in sizes that you can use, either slabs or blocks or bricks. So when we look at stone masonry, in terms of its symbols, these are the types of patterns that we would see for rubble, ashlar, or cut stones. Stones laid in irregular pattern with varying shapes and sizes, right? Irregular pattern, various shapes and sizes. Here's, you got courses of rubble. Here you have a wall that's a web. Ashlar, squared stone laid in patterns but no cut dimensions. See, they're laid in patterns but no dimensions. Whereas regular coursed ashlar, there's a consistent pattern. Stacked pattern. Cut stones are cut at a mill to dimensions and then laid according to design. So you've got, they're milled, and you can put them together in various patterns to get these shapes, and then you can repeat them. Masonry accessories. You have what is referred to as a bond beam, a special channel block with reinforcing steel and mortar and grout. That's this bond beam up here. It's the top wall, and it's got this channel here so that you can put bars in the horizontal direction and also vertically. Lintels are members in place in masonry walls above doors and window openings. So similar, a bond beam is a beam of concrete wall that locks the top section of all these walls of wall together. A lintel spans over an opening of a door, and it's very similar to a bond beam. Or joint reinforcement, or anchors and ties and rods used in the mortar of joints. So you can see that this bar represents a joint. It's a tie. It's a rod that's being used in the mortar joints, like here and here. Division 5 are metals. They're used extensively in construction. So we have metal studs, we have metal beams, we have metal joists, we have windows made of metals, we have doors made of metal, there's roofing made of metal, plumbing is made of metal, and then we have hardware made of metal. So Division 5 will refer to the certain types of metal. So maybe an exterior door is exposed to heavy moisture from the salt air. Well, then maybe stainless steel is more appropriate of a metal for the hardware than, say, aluminum. So we have types of metals. You have your ferrous metals and your non-ferrous metals. So ferrous metals contain iron as a principal element. They're usually magnetic, right? You can take a magnet and know if it's a ferrous metal. So iron and steel are ferrous. Non-ferrous metals, they don't have iron. They're not magnetic. So I can't take a magnet and put it on aluminum, and it's not going to It's not going to do anything. Non-ferrous metals are usually lighter. They're also less strong than ferrous metals. Aluminum, for example, copper, brass, and bronze. Although these metals are not good in terms of how would you say? They don't have the strength like the ferrous metals, like iron and steel, but they're softer, they're lighter, but they also can be conductive to electric. So aluminum, copper, brass, and bronze happen to be the ideal material when it comes to electrical components, because they are very conductive and they are lighter materials. Surface treatment. So sometimes material is treated with a coating like chroming. Chroming is applied as a finish to a metal surface. Galvanizing is a coating of zinc on iron or steel to resist rusting. But galvanizing is a zinc coating. So when you're welding on galvanized steel, the smoke from galvanized steel is very poisonous. So one who is a welder and who's working with building materials should be aware of that fact, because safety conditions and working with that material, there's safety hazards with working with that. Rusting is a protective layer of rust formed on certain steels. So rust can be a protective layer from rust. I guess once it's rust, it doesn't go all the way through. It provides a layer. I'm not sure. Electroplating is, but see, this rusting, we're talking about surface treatment. So making something with a coat of layer of rust and then putting like a finish on it. Or electroplating, which is adhering a metallic coating applied by means of an electrical current. So they have a magnetic paint. They can magnetize the material, spray it with a powder of a magnetic coating, and then applying heat to it where it'll melt, and then it turns into like a paint. So electroplating is a way of providing treatment. Metal gauge. The metal gauging system is metals that are less than 1/4 of an inch thick are classified by gauge and number. So once you go, oh, it's about an 1/8 inch thick. Well, 1/8 inch falls within the gauge category. So 0.125 is about 1/8 of an inch. So 0.125 is like a number 11. So and these are the increments in size. So gauge 4 is 224.2 thousandths. This is 194.3 thousandths of an inch. 16 gauge is 0.05 or 59.8 thousandths of an inch. I guess you could say this number when you want to, because I said point when the point is over here. So that's 598 tenths of a thousandth. Metals. You have your structural steels, you have your steel joists, you have your metal fabrications, and you have your decorative metal. So structural steel and steel joists, their joists are meant to carry load, span over distances. You have your structural steel, which provide the basic framing, vertical and horizontal structure. Then you have metal fabrications, things that just take raw pieces of metal, cut them to size, to fabricate objects, doors, openings, stairwells, fencings, gates. Decorative metal, again, maybe the gate is structural, maybe the gate is of security. You have your structural steel, right? Terms applied in hot rolled steel sections, shapes, and plates, and inclusive bolts, rivets, and bracings. So this is your steel I-beam. Notice that it looks like the shape of a letter I. It's a structural steel is hot roll steel. So this steel comes, when it's milled, it comes almost like it's in a liquid form, and it's extruded into that shape while it's like red, white hot. Like it's so soft, it's like soft as dough. Soft as, yeah, like a dough or a clay. But then when it cools, it hardens, and it provides a certain amount of strength and flexibility. So you have structural steel and your designations. So the height of this material, or is 12 inches. So this is considered a wide flanged beam, and it's measured from one flange, one flat area, to another flat surface, 12 inches in height, and along its length, 12 inches would roughly weigh 16 pounds per lineal foot. So for each foot of 12 inches of beam, have about 16 pounds of steel. Now that beam is an I formation. Here you have an angle iron, the angle being 90 degrees, or an L shape, and it has both its size, 3 inches representing the height on one side, 3 inches representing the length in another direction, and then its thickness. So when we look at the designations, see W 12 by 16 is telling me that it's a 12-inch wide flange by 16 being pounds per lineal foot, where L3 by 3 by half is telling me that the leg width, see, this is the leg of the angle iron. It's got two legs, 1 and 2. So leg 1 is 3 inches, leg 3 is 3 inches, and its thickness is 1/2 inch. These are the different types of steel. So you can see you've got your shapes, you've got your I beam or I channel, you have your American Standard beams, which are different in size. So this is where they called this the difference between a W and an M. The W is depth of 21 inches by 13 inches, and the M8 is 8 inches by 2¼ inches. Your American Standard beam, which they will call an S, the numbering system S by 23. Its nominal size 8 by 4. This is what they call a C channel. It's a channel, miscellaneous channel. L, you've got your 6 by 6, or you can have an 8 by 6. Here is a T shaped. This one also T-shaped, and this one a Z shape. Division 6, woods and plastics and composite. So wood has a high strength in compression and tension and is used for structural framing, your rough carpentry, your trim, floors, walls, and cabinetry for finished carpentry. So structural framing, rough carpentry, trim floors and walls, and cabinetry, finished carpentry. Here's an example of trim. Here you're seeing hardwood used on the stairs. Here you see wood being used in cabinetry. We have types of wood. These are different species. You learn as you go, but just know that these different species of wood have associated prices related to them. So usually you've got your hardwoods and your softwoods. Ash, beech, birch, cherry, elm, gum, hickory, mahogany, maple, oak, walnut. And you'll notice that each of these different materials will have their areas in the country, their regions in the country where they're more accessible. Softwoods, so like pine, ponderosa pine, southern pine. I'm going to see these more on the Pacific coast of the United States, whereas white pine or cedar, eastern cedar, you even have two species of cedar, one for the eastern portion of the country and western portion of the country, because these are different species of wood that grow in different regions of the country. And therefore, you may find these hardwoods and softwoods common in your area and more rare in other areas. Lumber classifications. So lumber can be classified as rough sawn or surface to size. Rough sawn is cut to size but not dressed or surface. The rough sawn or rough surface, here a smooth surface. So something that's rough sawn, more applicable to sometimes it's just for looks. So surfaces are finished to a size by running it through a planer, so they get smoother. Here you see the factory marks or the milling marks. Here it's gone beyond the rough and you've gone into more finished surfacing. So what began as rough can end up finished and surfaced. Now when you surface it, boards have multiple sides, right? 4 sides if you don't count the ends. 2 faces and 2 edges. So in order to do that, and your material is based on its price, and the price is based on the processes that are done to it, surfacing being one of them. So finish a size by running it through a planer. When you surface 2 sides, it's S2S. When you surface all 4 sides, it's S4S. Now, sometimes I'll buy material S2S. It's going to be one edge and one face that gets surfaced. It's not both flat surfaces. S2S allows me to do the other finishing or surfacing or joining on my own. Plywoods. Plywoods are made of layers of wood, and grain is positioned at right angles from these layers to provide strength. Odd numbers of layers of the grain and face and the back run in the same direction. Basically, you're just having layers crisscross each other instead of all running in the same direction. It provides some strength in the wood, in the panels. And they can provide you thicknesses from 1/8 to over 1 inch. Plastic composites, many used in construction, like plastic laminate, which you find on countertops or cabinetry. You have window casings, door casings, wall surfacing, they'll all have some sort of plastic composite. You have plastic gutters, downspouts, drainage pipes. You start seeing trim and other ornamental moldings made of plastics. You have glue laminated timbers. So where you don't have the ability to make a large piece of lumber from one tree, you can take pieces of the tree, glue them together to make a larger piece of lumber, which we would call a timber, right? So here we see large timbers used in the framing. This is actually timber framing construction. Well, these timbers could be milled from a large tree, or you can take the components of lumber and glue them together to make a larger member. So these could be glue laminated together as opposed to organically being formed by one tree. You can use the pieces of many trees to form that piece. And you can fabricate any size, beams, columns, arches. They can have shapes to them, and they provide strength, and they're made in a factory setting. Division 7 is thermal and moisture protection. So we're talking about roofing, damp proofing, and waterproofing. The thermal ability is insulation, providing weather barriers. Flashing and sheet metal help in providing those weather barriers. They also provide smoke and fire protection. So if there's a fire, these things won't catch on fire or produce toxic smoke. Or they provide protection to joint protection. The spaces, the cracks, the crevices. Notice this building is wrapped in a plastic paper. That's an exterior type of insulation or a weather barrier. It allows moisture to leave the building, but protects the moisture from penetrating the building. Here, this is insulation made to trap and provide a barrier to keep the warm air inside the building, or to keep the hot or the cool air inside the building and the warm air out. Here, you see these are basement walls, and the walls are being coated with a moisture vapor barrier. So water will not penetrate the walls, because where this guy's standing will eventually be filled in with soil. And so soil will eventually, water will eventually penetrate the soil. And this moisture barrier here will help keep moisture from penetrating the building. Insulation. It's used to reduce thermal transmission, right? The transmission of cold air or hot air. It's classified as flexible, loose fill, reflective, and rigid. So rigid is structural and non-structural. So non-structural meaning that it can't support the weight of the building, or structural where it can support the weight of itself or the weight of the wall. Here you see loose fill. It's loosely filled in the bag and they pour it out onto the floor there. Or it's flexible. Here it comes in the bat form. So like a blanket, you can roll it out. Insulation is measured in its R value. And R is a resistance to thermal transfer. And the R being the rating system. So examples of R values for 3.5-inch bat insulation, they'll get an R value of 13. Where 10 inches of cellulose that is blown in can give you an R value of 30. Whereas 1 inch rigid, that's like styrofoam, like a 1 inch insulation board, can give you an R value of 5. And these different size applications of insulation would be used in different applications throughout a building. Division 8, openings. So openings usually have to do with windows and doors. And so CSI's created a division all by itself for openings. So doors are addressed, any specialty doors, folding doors, entrance doors, storefront doors, curtain walls, windows, roof windows and skylights, the hardware, the glazing, which is the glass, and any louvers associated with those. Glass is a ceramic material formed at temperatures above 2,300 degrees Fahrenheit, made from sand or silica, soda, which is sodium oxide, and lime calcium oxides. So those are the components of glass and how it's formed. With other materials like dolomite, add for strength, and recycled glass called cullet. Float glass is the most typical. Over 90% of the world's glass is a flat glass. It's a continuous ribbon of molten glass that flows out of a furnace and floats on a bath of molten tin. So you've got a liquid bath of metal, tin, and then you take glass, which is also a liquid, and you pour it over a liquid tin, and it floats. Because it's a different density, it'll float on top of the metal like water, like floating on water. And that's how it gets flat. And then when it cools, the glass is separated from the metal because they don't mix. And that's how you have that flat glass. Irregularities will melt out, like bubbles and things. And glass is fired, polished, and annealed. So they can do it through a firing process again, and they can adjust the hardness and the polish of the glass. Bent glass is heated annealed glass that's passed over a form. So once glass is made, you can heat it up again and then bend it to a form. Safety glass is glass that is tempered, laminated, or wired. You can have 2 layers of glass with a thin layer of wire sandwiched in there, glued together. So now the glass has some wire reinforcing in it. And I think that's what we see here when we see these vertical lines. This is a type of glass with some metal wiring laminated. Or it can be tempered. It can be heated to a certain temperature that it's very hard. And so when it breaks, it fragments into tiny little squares. It'll shatter into tons of pieces and that are not as sharp. So that's what gives it its safety ability. And same with laminate. A laminate glass can crack, and it cracks, but because it has this glue sandwich or laminated between, when one layer shatters, it shatters, but it doesn't fall to the ground because there's some plastic that's laminating and holding it together, like a windshield on a car. You've got insulating glass, which helps provide some R value. You have pattern glass, which are cut into patterns to give you shapes and looks. You have stained glass, which also gives you some artistic looks. And they can be cut and shaped in a mosaic pattern, and that's usually called art or cathedral glass, like you can see here in this little window pattern, art glass with that gives you the shape of a branch and some birds and stuff. Or these front doors, which have this art glass into the doors. Or here you see these two layers, this insulating glass, providing an insulating value in this window. Or this particular glass, which has a pattern and it has a texture to it. Finishes. Finishes can be anything from carpeting, your gypsum wall, your ceramic tile, your paint, your different acoustic tiles like ceiling tiles. They're specifically defined on the room finish schedule and specifications. So finishes should be addressed in your specifications book, just to let you know what type of finishes and which rooms these finishes are going to be in. So this is an example of a room finish schedule, which is made up of rows and columns, or a list. And you can see that this particular list has a listing of all the different rooms that are numbered, the name of that room, and then the walls identified in the elevations. So you got your north, east, south, west facing walls, and the finish that might be on those walls. The same with so every room has walls, a floor, has base, and a ceiling. So you have different finishes for each different room. So the best way to organize all that information is on a schedule, a finish schedule to be exact. The major numbers and titles of finishes, so 09 being the category for finishes, but all these different finishes that we spoke about, they all have their own subcategory within Division 9. And we see that here. 0920 represents plaster and gypsum board. 0930 represents tiling. 0950 represents ceilings. You have this third row for information more specific than just tiling. So you might have multiple different types of tiles. So different multiple tiles will fall under 0930, and then these third column of numbers will be used to identify the different. So like ceilings, we have different types of ceilings. We have your acoustic ceiling, specialty ceiling, texture ceiling. So they all get their own category of, and so they're assigned their number, 51. Flooring, you have 060 for flooring, but then you have 61 for floor treatment, 63 for masonry flooring, 64 for wood flooring, and 65 for resilient flooring. The major numbers and titles of finishes. So again, 0960 flooring, you have your different kinds of flooring. You've got terrazzo flooring, carpeting, access flooring. You have wall finishes. So you have 0970 for wall finishes, 0972 for wall coverings, 0978 for interior wall paneling, 0980 for acoustic treatment. Now these numbers are very consistent, and these numbers follow their numbering format, Construction Standard CSI numbering format. Green building, way of reducing lumber waste. Pre-cut, custom, and fabricated components can be cut at a lumber mill, shipped to the job site, and that helps reduce waste. Gypsum wallboard and plaster, made of a core air-entrained gypsum between two layers of treated paper. So wallboard. Typical is 4x8 sheets. Custom size can be ordered in quantities. This is what we call sheetrock. Gypsum board. Or sheetrocks. These are different boards. You've got your regular drywall. You have moisture resistant. You have foil back. You have fire resistance. You have abuse resistance, soundproofing, cement board, square and tapered edge. You have your common thicknesses from 1/4 inch to 5/8 of an inch. Ceramic tiles. You have quarry tiles. You have mosaic tiles, paver tiles, metal tiles, stone tiles, concrete tiles, brick tiles. Basically tiles made of different materials. These are all the different ways of those tiles. You have your tile setting materials. So tile can be set in Portland cement, or it can be laid in with a latex adhesive or an epoxy mortar. Sometimes they call it thin set. Tile can be set in a thin set. But that thin set can be made of Portland, latex, or epoxy. Now the joints between tiles, or even between blocks, is called grout or mortar. A grout is a type of mortar. So this is some illustrations showing you an installation on plywood. So here you're seeing a section showing you the layer of plywood, then a continuous backer board, some sort of cement sheet, and then a bond coat here, a little layer of thin set, and then here is your ceramic tile glued to that, and then your spaces filled with grout. So this is showing you ceramic tile installed on plywood. Here's what ceramic tile installed on concrete would look like. Again, a section. This particular area representing a concrete slab, right? This particular pattern representing plywood. Green buildings or high efficiency windows. High efficiency windows are now made of triple glazed for cold climates. They reduce heat loss. They help keep the cool air in and the hot air out, or they help keep the warm air in and the cold air out. It just depends on the season. Double glazed are for warm climates. So this is high efficiency. This would be a higher efficiency. So better for weather conditions, it meets code requirements. See, so double glaze may be called for by code requirements. Here are some different types of flooring. You've got resilient floor, you've got wood floor, you've got carpeting. These are the symbols of what the floor would look like in an illustration. More symbols of what the material would look like in sections and illustrations and plans and sections, elevations. Green building technology. Here's an example of a live living roof. It's a construction method used to build more efficient structures, right? Also known as sustainable design. Things that are sustainable means that you can do it over and over again without hurting the environment. Benefits of green building. They protect the ecosystem. They help improve the air and water quality. They help reduce material waste, and they reduce building and operating costs. Green building technology. What does it mean to build green? Simply put, it means to design and construct energy efficient buildings that are made of sustainable materials and engineered to have a minimal environmental impact. Site selection starts with site selection. Remove as few trees as possible. Control erosion. Control water runoff. So when we're thinking about building, we want to think about where we're going to put that building. We want to think about removing as few trees as possible. Trees provide oxygen. Oxygen is good for us. The world is cutting down all the trees. We are having a large impact on the ability for the earth to produce breathable oxygen. Site locations. We want to be able to control erosion. We want water to run off and not damage or hurt the topsoil. We want to be able to control the runoff, being able to make water run off and travel in the direction that we want. We want pervious concrete use to reduce water runoff. So basically, I want concrete that water will go through the concrete and into the ground, not continue to roll downhill. Landscaping plants that are selected based on the local climate. So I don't want to have to water my plants if my plants can get their water naturally from the environment. Energy efficiency. I want to be able to analyze shapes of a building and orientation to the sun to help reduce cost, right? Being able to position the building so that it warms up naturally or stays cool naturally. I want to use well-sealed windows with low thermal transmission. Basically, windows help with low thermal transmission, help keep the building warm or cool. Interior windows help save lighting costs. By having windows located in the right space of the room, they let natural light in so that I don't have to turn the lights on in the room when not necessary. Efficient lighting system use sensors to switch off unneeded lights. So I might have ambient sensitive light system that says when there's not enough natural light coming in from the windows, then automatically turn off. And then have a sensor in the room that senses that there are people in the room by movement. If there's no movement or people in the room, then there's no purpose for having lights. So just the lights can automatically turn off to help save energy. When I'm selecting material, recycled or renewable materials help conserve natural resources. Avoiding material that emits volatile organic compound, VOCs. Some of the paints and finishes emit a volatile organic compound, or VOCs, and that escapes into the environment and it's not good. So sometimes paints and products are made with low VOC counts. Also, sustainable materials maintain long-term building performance. So engineered lumber or steel, they can help provide longevity to a building. Clean water efficiency. Being able to have clean, plentiful water supply is very important. And roof runoff water can be used for toilet flushing, gardening, and irrigation. So that water doesn't just roll off and go into the ground, into the runoff. You can capture it and use it for toilet flushing, for irrigation. You can use energy efficient plumbing fixtures and appliances. So fixtures that help save water. Green building, volatile organic compounds, so VOCs. They're toxic substances that evaporate into the atmosphere. They're harmful to the environment and to health, right? Breathing this stuff can give you headaches, make you nauseous. It can damage your organs and give you cancers. So using products with low VOCs not only are protect the environment, but they protect the health and welfare of the individuals. There's research building materials. So you look for other organic alternatives. So it's just saying research. Try different materials. Try to use materials that are organic that you can use as an alternative. LEED building. LEED is a leadership in energy environment design. So a building could be a LEED design building, meant to be greener, meant to provide some assurances that categories for green building are being used, and it's measurable. So you have 4 certification levels of a building. It can be certified silver, gold, and platinum. So a building that has high LEED standards, platinum, is taking into account every possible aspect of energy efficiency. LEED building certified categories: you have your integrative process, you have your location, your transportation, you have sustainable sites, your water efficiency, energy and atmosphere, materials and resources, you have your indoor environmental quality, you have innovation and regional priorities. So these are the different categories that are used in a LEED certified building. So that's basically it for this unit. Take this time, next 20 minutes, and go over the test your knowledge in the question textbook. Those are the answers. That's basically it. If you have any questions regarding this subject and this topic, send me a message in the Canvas inbox. Thank you.